have, right? So yesterday we have seen what is attention mechanisms. Also, we have seen a couple of you can say outputs or the results of the attention mechanisms when it is combined with convolutional neural network, how it is localizing to the important regions and suppressing, right? Or focusing or suppressing the focus of other regions and all. That is what we have seen. So today we will discuss the mathematical concept behind these attention mechanisms and what are the different types of mechanisms we have, attention mechanisms. Most popularly, I mean, there are two types of attention mechanisms you might have also encountered while going through some of the research papers and all. So those are nothing but channel attention and spatial attention. We'll see what are channel attentions, what are spatial attentions, and how to even combine the channel attention and spatial attention together, right? And what is the benefit of combinations and all. We have also seen, I mean, you can say the results of all these kind of attention mechanisms yesterday, and today we will mostly discuss the mathematical concept behind all these attention mechanisms. I think what we have discussed yesterday, that any attention mechanisms can be treated as a dynamic selection process, right? And that can be realized by adaptively weighting the features according to the importance of the input. So what exactly this statement says, we'll also discuss while, right? I mean, when I will discuss something called as channel attention, right? So this part already we have discussed, if you remember. Already we have seen a couple of examples and the importance, the effectiveness of the attention mechanisms when it is coupled with convolutional neural network. So what we have discussed also this one, right? So basically, in general, it is of two types like channel attention and spatial attentions, right? And also we have seen something called as a squeeze excitation network. And there are also attention mechanisms which combines both the channel attention and spatial attention, which is nothing but CBAM is a very popular attention mechanism which combines both spatial attention and channel attention together. So I'll start my discussion with the channel attention first. So before I discuss channel attention, let us try to formalize something called as attention mechanisms, right? So any attention mechanisms can be expressed mathematically with the help of this particular equation you can see over here. So it is f of g of x comma x. So x is nothing but the input. It could be the image. It could be any feature map. That could be the feature map that has been obtained using some convolutional operations, right, in the convolutional neural network. And this g of x is very, very important. And this g of x is nothing but the learnable weights. So these are like the weights, and these are like, this is our input, and these are like the weights or learnable weights. And what I want ultimately, that I want to get a weighted output, or you can say the weighted version of the input x. So it could be x days, right? So what I'm currently getting is x days, and I can call this as a refined feature map. So the goal, I mean, x is an input feature map, right? So it could be having size H cross W cross C, right? You might have seen in convolutional neural networks, after applying convolutional layers, right? You'll be having some height. I mean, you'll be having some spatial resolutions, having height as H, and the width is nothing but W here, and C is the number of channels. That means the number of times you have applied the filters. You might have seen also this kind of outputs, right? If you remember, we have seen yesterday also this kind of outputs, right? Where this particular size is nothing but this can be considered as H, this can be considered as W, and this is basically the channel, right? So what I want to apply the attention over this particular feature map, and this could be considered as X, right? And what I want ultimately, that the output should be a refined version of this input, right? Where my model will only select the important features either in the spatial dimension or in the channel dimension, right? So there are features in the channel dimensions here, and there are also features in the spatial dimension. You can see over here, right? So my task here is to dynamically select the important channels as well as the important positions, and based on this, the name is so-called channel attention and spatial attention. So this is X. So what I'm planning to do here is, I want to apply F here. F is nothing but the attention over here. You can say any attention if you want to apply over here. And what I want to get is X days. And X days is a refined feature map of the corresponding X. The size, even after applying attention, is going to be same. right? So what we are trying to do here is we are trying to generate some weights and multiplying these weights with this input, and finally what we are getting is x days. But these weights, we don't want to fix these weights. These are like, adaptively weighting mechanisms. So that means, that is why I'm saying that these weights has to be learned, right, by the model itself, right? And that weight will decide whether I should give more weightage to a particular position or particular feature or not. And based on that, I want to just select some of the important positions, some of the important channels, right? When I say important channels, if you want to highlight, that is channel attention. If you want to highlight some important positions, then it is known as spatial attention, right? So now you can see this g of x is nothing but the weights or the learnable weights, and this x is nothing but the input. And after getting these learnable weights, what you can do is you can just perform, you can either perform a dot product, or sorry, not dot product, element wise product, or a cross product, right? We'll see. I mean, it varies from the attention mechanisms to different attention mechanisms to attention mechanism, right? So we'll see in details, right? You can see this is the squeeze and excitation mechanism can be denoted like this. So let us first discuss what is squeeze and excitation, and then come back. I will then come back here, and then we'll see whether we can represent this squeeze and excitation in terms of this particular equation or not, right? Now let us first talk about the channel attention. And squeeze and excitation is one of the very popular and the first channel attention mechanism that was published in 2018 in CBPR. CBPR is the best conference in the field of computer vision and pattern recognition, right? Fine. So you can see over here how actually this channel attention is working. And what do you mean by this channel attention? Just now we discussed, right? Because not all the channels in particular feature map contains important information. Here, this is height and this is width and this is channel, right? Now, the orientation is different, right? I mean, the way I have shown, and here it is something very different, right? I mean, but it is again S H cross W cross C. There's a 3D map, right? Fine. So what I'm trying to say here is we are having C number of channels, and we want to highlight only the important channels, because what we know that not all the channels carries important informations. So how to highlight the important channels and suppress other channels? That is what is the major goal of the channel attention mechanisms. So what I ultimately want here is I should have C number of weights, because I am having C number of channels. I should have C number of weights, 1, 2, and so on up to C number of weights. And these are like weights, let's say, like these are weights, different weights I am having, right? And I want to just find out the C number of weights. I want to make it learnable, right? I don't want to give some fixed values because I don't know that which channel carrying important information. And then I want to multiply these informations with each of the channels that are present over here. That is what I want to do here. So how to do this? So in squeeze and excitation, right, paper, they suggested to get this 1 cross 1 cross C. That means to get the C number of channels, what they've applied is a global average pooling over here. Over this input, they have applied first global average pooling. That means for every channel, you will get a single value. With respect to every feature map, right, you will be having C number of feature map. So if you are applying global average pooling, that means you will get a single value here. Again, for the second channel, you will get a second value. C number of channels, you will get C number of values. And those values cannot be directly considered as weights, right? Because these are not learnable. We don't know whether these weights are going to be helpful for us or not. To make it learnable, either you can use a fully connected layer here, or you can use a 1 cross 1 convolution over here. 1 cross 1 convolution. In squeeze and excitation, they've applied 2 times 1 cross 1 convolution, or FC layers, and followed by a sigmoid activation function. Sigmoid activation, right? So after applying sigmoid activation function, all these weight values will be lying from 0 to 1. That means these are like the weights, the final weights, right? And these values, after getting the weights or after applying the sigmoid activation function over here, what you will do is you will multiply element wise, right? I mean, each value will be multiplied with each of the channels or each of the feature maps here, because we have C number of feature maps. So here, every weight is going to be element wise multiplied with each of the feature map. And then finally, what you will get is nothing but, here it is X bar, right? Which is nothing but the refined or the attention feature map, right? This is what is known as squeeze and excitation, where we have first applied global average pooling to get C number of values. Because we have C number of channels, we want C number of weights, and then to make it learnable, they have applied different convolutions, one cross one convolutions, or two different fully connected layer over here, right? And then they have applied something called a sigmoid activation to have the weight values in between 0 to 1. Then whatever the values you have obtained, that can be considered as the weight and will be element wise multiplied with each of the feature maps. That means with C number of feature maps. And the kind of output which you are getting is again H cross W cross C. There's no change in the size, but there are, of course, I mean, you can see that these features are, of course, the refined features where the focus will be only goes to the important regions, or especially the important channels here, right? Important channels. And that is what is channel attention. You can see this is the procedure they have followed. Global average pooling, followed the one cross C, followed by fully connected layers, two fully connected layers. First fully connected, this can be easily replaced by one cross one convolution. If you want to make it fully convolutional network, you can just replace this fully connected layers by the one cross one convolution. And then at the end, as I mentioned, that you have to use a sigmoid activation function, and you'll get again one cross C number of values, basically C number of weights, and that is now multiplied with this input X, and what you are getting is again X bar, right? So that is what is the task. And now if I want to represent the same thing with the help of the expression, which I've already shown you, right? So how to get this G of X? What is this G of X? So this G of X is nothing but this one, after getting the weights, right? So how to get this G of X? First, let's say this is X. So I'll apply first global average pooling, then convolution, then sigmoid, then what I will get is nothing but these weights. And these weights is now going to be multiplied element wise with this X. And what you will get is ultimately X dash or X bar, whatever, right? You see here how to get this G of X, the learnable weights. It is first, this is the input. Then we are applying, of course, here global average pooling. Followed by this MLP means these are like, 2 times FC or 2 times convolution, one cross one convolution, 2 times, and then sigmoid to get the weights. And now the weights are now multiplied with this X. This is the element-wise multiplication. This can be also written as G of X, element-wise multiplication with X. And what we are getting is X dash or X bar, right? This is the output. The output after applying the channel attention. There are different types of channel attention mechanisms proposed over the years, but this is a very, very popular one. If you want, you can go through the literature and you will find also other types of attention mechanisms. I mean, channel attention mechanisms. People have also applied Fourier transform, discrete cosine transform to design, right, the channel attention. So here you can see the results of the SE net compared to other architectures is really better. I mean, convolutional neural network with attention is really performing well compared to the only convolutional neural network. We have also seen the results, some of the visual results yesterday. I'll also show you a couple of other results today. Now let us again discuss what do you mean by spatial attention. Just now we have seen how to select the important channels. Now we can say how to select the important positions, right? What we have seen, right? This could be H, this could be W, this could be C, right? This is S cross W cross C. Maybe the output feature map after applying some convolutional layers and all, fine. This could be taken from anywhere in the network. And now on particularly this feature map, we can apply channel attention over here. So I'm right now discussing what is spatial attention, and then we will see how we can combine this channel attention and spatial attention together, right? So in case of spatial attention, what we are actually trying to do is we want to select the important positions. These are the spatial positions we have, right? And we have C number of such C number of feature maps which are stacked together and look like a 3D feature map over here. So for every two-dimensional feature map here, you'll be having the positions, and the resolution is H cross W. I want to highlight only important positions and suppress the other positions because not all positions are important for particular applications. So how to do this, right? How to do this? Again, we need to multiply something. That means again, we need to prepare something called as a weights corresponding to each of these positions, because now I'm looking at the positions. In case of channel attention, if you remember, we were having C number of channels and we have obtained C number of weights. But in this case, we are having H into W number of positions. So I should have also H into W number of weights. So weights can be also having size H cross W plus 1, right? So this should be the size of the weight matrix, and this can be multiplied with each of the feature map element wise, and what I will get is nothing but known as x dash, right? So this has to be, these are like weights, and this is the input x, and this will be multiplied element wise to get this x dash. So that means this g of x in this case is nothing but this one, and this will be multiplied element wise with this x. Now the question here is how to get this g of x, that means these weights, right, from here, from particularly this feature map. So to get the weights, right, having size h cross w cross 1, what we can do here is we can apply this global average pooling or max pooling, whatever, along the channel dimension, right? So that means every position is having c number of values. You can see every pixel is having c number of values along c dimension, along the channel dimension, you can say, right? Because it's a c dimensional, you can say, you can consider every pixel here or every point is nothing but a c dimensional point. So that can be averaged, or that can be, right, you can apply global average pooling across the channel to get to get actually a matrix having size h cross w cross 1. And then what you can do is you can apply a convolution operation over here, maybe of size 1 cross 1 convolution, for example, and then you can apply sigmoid activation, right? This followed by this cannot be directly called as, so this, if you apply cos, or you can say if you are applying average pooling across the channel, right? Average pooling across the channel. I can call it as a global average pooling, but it is across the channel, right? It's not across the feature map, it is across the channel. So then you will get this kind of output. And then you are applying, let's say, 1 cross 1 convolution followed by a sigmoid. And finally, what you are getting is a weights, set of weights having size s cross w cross 1. So now these values will be directly or element wise multiplied with each of the feature map here. And what you will ultimately get is nothing but x dash. And that is what is spatial attention. And you can also obtain spatial attention using various approaches. That's the simplest approach you can follow to get this spatial attention map. In 2018, in another conference, a STAR conference, ECCV, there was a paper, right? So there's a approach attention mechanism known as CBAM was proposed, convolutional block attention module. But this is how actually the CBAM looks like. You can see over here. As the channel attention is applied, and whatever the output you are getting, right? I mean, kind of X days you are getting over here. And again, the spatial attention is applied over X days to get X double days. So that means here, channel attention is first applied, followed by the spatial attention. Later, people have also applied channel attention and spatial attention simultaneously. I mean, parallelly, what I'm talking about. Here is, of course, there are certain questions that may come to your mind, that why channel attention first, why not spatial attention, right? So that also you can explore, that whether channel attention should be applied first or spatial attention should be explored first, right? And where to include these kind of attention mechanisms into the convolutional neural network. So what they have claimed in their paper, in CBAM paper, that this attention, basically the combinations of the channel attention and the spatial attention, is really performing well compared to the only channel attention, which is nothing but known as squeeze and excitation. You can see over here. I think yesterday also we discussed the same. We have discussed, and we have also seen a couple of examples where CBAM was performing well. You can consider any example, right? Here CBAM is performing well compared to the only channel attention, which is an excitation. You can also look at this particular image, snow leopard, right? Localization is really better in case of CBAM compared to the squeeze and excitation you can see over here. And if you go through the literature, you will find multiple attention mechanisms that have been proposed over the years based on channel and spatial attention concept, right? There is one more attention. There is one more attention which is recently very, very popular, which has become, you can say, the most popular attention nowadays, and is also played a very important role, or you can say it is also considered as the core component of something known as Vision transformer models, right? Vision transformer models is a very powerful model nowadays, and you'll find a lot of foundational models of, related to this Vision transformer and all, which are also currently being adopted to medical imaging domain. So in heat, the major component, or you can say the basic component in vision transformer is nothing but an attention mechanism, and that attention is something very different from the attention which you have seen just now. And that attention mechanism is known as self-attention, right? Self-attention, and these attention mechanisms helps in obtaining the global relationships, right? That is present within the feature map, because the kind of attention mechanism which we have seen just now is like the attentions. You can say, you can consider all these kind of attentions are local attentions, right? But this kind of attention is very, very helpful in capturing the long range dependencies, or I can say the global contextual informations that are present in the image. And this is a variant of the self attention mechanisms which I have taken from this paper. But if you go through the vanilla VIT architectures, you will find the architecture, or you'll find basically the self attention architecture a little bit different, which is initially translated where all the feature maps, because VIT works on the patches rather than the whole image, and there is also a stage to linearly transform those patches into a vector, and those vectors will be initially transformed into three different parts like query, key, and value, right? But while transforming all those patches into a one-dimensional vector, we know there's a possibility that we may lose some of the spatial information. But this is the paper where it has been mentioned that if you want, you can also apply self-attention over the feature map, which is, right, having size H cross W cross C directly, right? So how is it possible? Initially, you may apply some convolutional operations like 1 cross 1 convolutions to have three projections like key, query, and value. And then what you can do, you can find out the pairwise relationship. If you remember, in case of additional channel attention, the weight is one dimensional, right? It is like 1, 2, and so on up to C. It is 1D. And in case of spatial attention, it was 2D. If you remember, the weights, right, is having size H cross W cross 1, if you remember. And in this case, the size is a 1 cross 1 cross C. But in this case, in case of self attention, the weights I'm talking about, right, these are like G of H, the weights, right? The weights is 1D in nature in case of channel attention, and the weights is 2D in nature, that is H into W into 1 in case of spatial attention. But in this case, the weight is something very, very different. We call it as a score, and the size of the attention score metric is something very different from these two. So here we're trying to find out the pairwise relationship. So when I say HW cross SW, obviously, the computational complexity is really high here. Let's say, for example, you are, after applying some convolutional operations and some polling operations and all, so what you are getting is an image or a feature map is having size 7 cross 7 cross 512, on which you are trying to apply, let's say, channel attention. And then in this case, the channel attention weights is going to have the size 1 cross 1 cross 512. In case of spatial attention, this is spatial attention, right? In this case, the weights, right? I'm talking about weights only, weights and the weight scores, right? So in this case, in case of spatial attention, the size will be 7 cross 7. And what I'm trying to say here is, in case of self attention, the size is 49 cross 49. So we are having total 49 positions. And what it is trying to say is that we'll be having 49 number of rows and 49 number of columns. That means what we are trying to find out here is how one pixel is related to every other pixels within the feature map. That means we're trying to find out the global relationship over here, right? Because we are having 1 to 49 number of pixels, and here also we are having 1 to 49 number of pixels. And what we are trying to find out how the first pixel is related to all the pixels. And here we are not going to use any sigmoid activation function. Rather, we are going to use something called as a softmax activation function, right? Either the point will be related to this point or this point or this point. And if you add the values, you should get the value 1. That means row wise, if you add the probability values, so you'll get 1. So that means we're applying softmax here along the rows, right? So this is, we are trying to find out the pairwise relationship over here, right? That is how actually, I mean, we computed self-attention here. We'll be having three different projections, Q, K, and V. So this Q is having size, let's say H cross W cross C. After applying 1 cross 1 convolution, if you want, you can make it C dash, where C dash is less than C. That is also possible. If you want, you can also make it same, H cross W cross C. Then you can reshape it. You can reshape it having size, let's say HW cross C, and you can again take this second projection, which is again which can be again reshaped to HWC. If you want, you can make transpose also. This is K matrix, or you can say this K projection can be transposed to get the value C cross SW, and then you can just multiply these two to get SW cross SW, right? So what I'm trying to do here is I've just multiplied Q is a matrix, K is a matrix. I've taken the transpose of it, and then what I'm getting is this one, right? And then I've applied something called the softmax function over here. It is QK transpose, and then there can be a normalization factor over here that also you can add. And then what I'm trying to do here is then I'm multiplying again V with this, right? I'm multiplying V is another matrix over here. Again, it is having size HW cross C after reshaping operations and all. And what you will ultimately get is H cross W cross C. And if you have changed, let's say, the number of channels you may get here as W cross C dash, and you can use 1 cross 1 convolution to get back, and you can again perform reshape to get back to the original output size having H cross W cross C. Right? So this is actually what is exactly the self attention is all about. The idea is to actually compute the pairwise relationship among all the positions, right, that are present in the feature map. That is what you can do over here. That is self attention, the core part of vision transformer models. Right, over the years, people have also modified self attention mechanisms because it takes a lot of time, because this matrix computation is really a time consuming process. So people have also thought of reducing the time complexity of the self-attention mechanisms, and a different variant of self-attention mechanisms have been proposed over the years. If you want, you can go through the literature, you will find the variants of the self-attention mechanisms people have proposed, right? Even as I mentioned here, in traditional self-attention, it is also a kind of spatial attention, right? That is why I mentioned somewhere that again self-attention comes under the spatial attention category, but here we are trying to find out the pairwise relationship, right, instead of finding out the only relationships within the positions and all. Fine. And I'm not interested to go into the details of this beat architecture, which is very, very popular, right? And I already discussed actually where I mean how the self attention is playing an important role in VIT architectures, especially vision transform architectures. You can see over here, initially the image is split into number of patches, and all these patches are flattened, linearly projected. With there are some other things like position embeddings and all, and that all these things will be passed to the transformer encoder. That is where you may find something called as self attention inside here. This is how the encoder looks like. And this consists of multi-head attention. This multi-head attention is nothing but applying self attention multiple times and concatenating the results of each of the self-attention mechanism, and then ultimately what will be having a MLP head and followed by a classification head to get the class values for each of the class. Right. That is how actually we used to solve the classification problem with the help of vision transformer models. And this vision transformer models has been adapted from the transformer model that has been initially proposed in natural language processing task. That also you can go through. There also you will find something called as self-attention. You'll get a different view of self-attention by considering text examples. But here I've considered the image of the feature map as an example. And this particular part has been right taken from this paper, self-attention generative adversarial network. And here are the authors, so very popular authors like Goodfellow, Dimitris. I also got the opportunities to meet these guys, right? So recently. Fine. So I mean that's all about actually different types of attention mechanisms. I mean very popular types of attention mechanisms. We have channel attention, spatial attention, self attention. We discussed, right? And as I mentioned, that we have also proposed a couple of such attention mechanisms. You can go through my profile and you can find several types of attention mechanisms we have proposed since last 3-4 years, and we have applied it to medical imaging domain. And it is really working well. Most of the for most of the attentions we have released the code on the GitHub and all. And if it is not available, you can write to us and I'll share the code with you. You can also apply those kind of techniques into your problem statement if you're dealing with any image and video centric tasks. So it can be also applied to any field. So this is one of the attention mechanism which we developed in 2021, and this paper was published in 2022 ICIP conference. Right. So here basically what we did is we published something called as we developed something called as a channel split dual attention. You can say mechanism where we have initially split the whole channels into two parts, and then we have applied position attention as well as the channel attention, right, together, I mean parallel, you can say, over each of the splitted feature map, right, along the channel dimension. And the kind of results which we have got is really interesting. You can see over here we have compared with squeeze and excitation as well as CBAM, the two very popular attention mechanisms which we discussed today. And you can also look at the results of our approach, right, compared to C and CBAM. You can see over here, there's a little bit of improvement in each of the case, right, compared to, we can say, both CBAM and squeeze and excitation. And here also, here are some of the visual results I think we discussed yesterday. So I can skip it. Yeah, here is also some of the results of the different attention mechanisms that has been taken from this paper. A cross-lesson attention network for accurate diabetic retinopathy gradients. You'll find its applications, right? Extensive applications of attention mechanisms in medical imaging domain, right? Here is another attention mechanisms or another self-attention mechanisms which we proposed, and we have validated it on histopathological images, which is mainly used for breast cancer classifications in our case, right? I don't want to go into the details of this histopathological imaging and all, right? So this was the task actually which we solved, for which we developed something called as a kind of self-attention mechanism, deformable self-attention mechanism especially. I'll show you what we have done. So basically, this convolutional neural networks, what we have studied till date, is very good at capturing the local informations, and these are not good at capturing the global informations, right? Because convolution itself is a local operation. So then how to deal with this kind of problems? At the same time, it is, I mean, why CNN cannot capture this global information? Because of the limited receptive field it is having, right? Even if we are having multiple number of layers, but the limited receptive field, right, creates the problem to capture global informations, right? So VITs are very good at capturing these global contextual informations because of the self-attention mechanisms, right? But VITs also demand huge amount of parameters compared to the convolutional neural network that sometimes even restricts ourselves to use VITs in the domain of medical imaging, where getting, even obtaining or collecting multiple images or millions of the images is really a difficult task, right? And but VITs are very good at capturing the global information, but again it falls short of capturing local information. So CNN has some advantages, VITs has some advantages. So then people have just, if you go through the recent literature, you will find people are combining both CNN and VIT together to have the strength of both CNN and VIT, right? So one is good at extraction of the local information, one is good at extraction of global information. So why not to combine them together? So that's what actually we did in 2023. I hope the paper is published in 2024, right? So what we have done here is, initially we have extracted the information of the multi-level features from a backbone CNN architecture, and then we have introduced something called as a residual deformable transformer layer. Especially, we have developed something called as a multi-head deformable self-attention. You can see over here, right? So what we have introduced and right is nothing but deformable convolutions, because the kind of lessons which we are actually dealing with in this particular problem, they are varying in size and shape and all, and deformable convolutions are very good at, right, capturing those sizes and shape variations. So that's why we have introduced deformable convolutions into these self-attention mechanisms to project the input into different projections like Q, K, and V, and then we have applied something called as a softmax to get this prioritized relationships or to get the attention scores and all, right? So at the same time, you can see this is actually the transformer layer which we have proposed, right? So it consists of mainly the multi-head deformable self-attention mechanism, where we have applied the proposed attention several times, and then we have concatenated. Yes, we have just combined the results obtained from all these heads. All right. So when I say head, it is like head one, head two, head three, like this. Right. So let me show you some of the interesting results which we have obtained, and when we have compared with squeeze and excitation, there's a BAM which combines both general attention, spatial attention. There's something called as a categorical attention. There's something called as self attention, which we have seen. So you can now see how our model, especially right, the proposed attention is performing better or outperforming other competitive, you can say, attention mechanisms, right? You can see over here there's a change of the values here, at least by 2 to 3%, right? If I compare our proposed attention with the self attention mechanism which we have modified, right? So you can also see its effectiveness of this proposed attention mechanism from the visualization results. So you can see over here, these are red marks, red arrow marks provided by the doctors, especially the pathologists, right? And here are the regions which we are looking for. That means these are the pathological regions. And if you see the model without the proposed transformer layer could not even able to right focus in on these parts. These are also pathological regions, but you could not able to identify this. But now with the use, or you can say introduction of this deformable self attention mechanism, the model could able to identify. It is still not precise, but yes, at least it could able to identify all the regions, right, accurately. You can see over here. So that is how you can find the difference of your mechanism with other mechanisms, and what is the role of the attention mechanisms, whether it is self attention, whether it is other types of attention, doesn't matter. So how actually it helps in improving the focus, or the you can say how the model is emphasizing on the important regions and suppressing its focus on the unimportant regions is also really very, very important. With this, right, I will just you can say end the session on this particular attention mechanisms. But next, I will start our discussion on the very important topic in medical image analysis, which is nothing but you know image segmentation, medical image segmentation, right? So let me open the PDF or the PPT first. Yeah. I hope it is visible and I'm audible also. Let me choose some color. Yeah. So this is actually the main focus uh, of today's session, that can we design deep learning models for solving medical image segmentation task, right? So in the title I have just mentioned it is image segmentation. That means on the I've chosen such architectures which can be applied to any imaging domain, including the medical image, right? And we'll see the most of the most of the architectures were initially validated on the medical images and later been adapted to natural image, right? But what we've seen in early cases, that initially this AlexNet, this GoogleNet and ResNet was applied to the natural domain, and later those architectures have been adapted to the medical imaging domain. But here you will find something very different, because this image segmentation is very, very important in case of medical imaging, where sometimes your task maybe is to highlight the tumor region and then tell the details about the tumor, probably the size, the volume of the tumor, right, that is present in the brain or somewhere else. So that is why the segmentation is one of the most important applications in medical image analysis. We'll see how important it is and how to solve the problem with the help of the deep learning architectures, because we have seen the disadvantages of the traditional learning approaches, right? So can we, and also we have seen the importance or the effectiveness of the deep learning approaches, right? So can we design the deep learning models, especially the convolutional neural network based models, to solve image segmentation task? Or can we use directly the kind of architecture which we have seen for classification to solve image segmentation or not? And how this task is different from image classification also, we will see. So before that, I'd like to ask if you're having actually any queries on attention mechanisms, you can write them in the chat box, right? And I will also check, right? Parallelly, if you're having any queries, I'll try to get back to you right? Or I'll try to answer all those things, because attention is a very, very powerful technique, as we all know. We'll also see the applications of attention mechanisms in solving image segmentation tasks. So if you're having any queries, feel free to write in the chat box. I'll read it and try to get back to you, simultaneously. Fine. So here is the content actually which I'd like to cover in this particular session. I'll start with definition of the image segmentation, of course, because I don't know what is your background and all. And then the types of image segmentation, and then what is very important for us, why do we need the learning-based segmentation methods, and what are the state-of-the-art models, or you can say what are the state-of-the-art convolutional neural network as well as vision transformer models we have for solving image segmentation tasks. Fine. Okay, so I'll start with I'll start with considering some natural images, but slowly we'll move towards the medical imaging domain as well, right? So it's just, I mean, if you just change the image, right, to medical imaging, so only the output is going to be different, the model may be the same, right? The same model can be applied to natural image, the same model can also be applied to medical imaging domain. We'll see in detail, right? So what do you mean if somebody will ask you that, yes, can you define image segmentation? So what is image segmentation, right? And how the outputs of the segmentation of an image looks like, right? Is it a single value or is it a single label like a classification task? No. The output in case of segmentation is also an image. You can see over here. So when I'm trying to define image segmentation, it is nothing but, right, partitioning the image into multiple segments or multiple objects. You can see over here. So this is an input image, right? There's a person who is riding a bike, and I want to only highlight these objects, the person and the bike. I don't want to focus on other regions. I want to only highlight these regions. I don't bother about other regions. So this is one of the segmentation tasks where you want to segment or you want to partition the important objects, which is nothing but a person and a bicycle or a bike here, right? So maybe in this case, you can look at, in this case, you can only focus on this horse and there's a person over here, right? You can see here, this is the output which I am looking at. Also, you can, if you want, you can focus on some of the cars which are having. So you can also focus on this. So simply partitioning the image into different objects of our interest, right? And these objects, may belong to a single class. Like in this case, you can see both of them are cows. So they all belong to a single class, right? So sometimes it may also belong to different classes. You can see different colors we have given here, right? For different class, for horse, different color, for person it's a different color, for car or for vehicles it is a different color, right? Sometimes it may be same, it may be different, right? That could be different class, right? That may be, I mean, there could be different objects, you can call it as, right? That may be present in an image. We'll see later on. So there's a lot of applications, not only in the field of medical imaging, as I discussed, it has also applications in autonomous vehicle, video surveillance, scene understanding, and a couple of other fields in computer vision. Now let us try to differentiate the very important problem statements, right, which are nothing but classification, object detection, and image segmentation. You might have also heard about this term so many times, right? Because deep learning has vast amount of applications in these kind of or on these kind of tasks. So when I say classification, that means given an image or cat image over here, your task is to just assign a level. So classification, what we are trying to address is what is in the image. That means you want to ultimately assign a label with respect to a particular image. That is what is classification. But classification is localization is something a little bit complex. And you can say, if the classification says what is in the image, your job is to only assign a level. But in case of classification with localization, you have to address what is in the image, that is the cat, and where exactly it is. That means you have to also provide a bounding box where there is a cat in the image. That is classification with localization. Object detection, if you see here, there are different types of objects in this particular image, and your task is to address what are all the objects that are present in this image and where are they. You need to first tell what are all the objects that is an image, like dog and cat, and where are they. You need to also provide the corresponding bounding box for each of the objects that is present in the image, and that is what is known as object detection. But segmentation is something very, very different from all these tasks, from classification with localization, and object detection, right? So in case of segmentation, your task is to, address what type of object is each pixel in the screen. So that means every pixel in the image will be classified to different objects what we are having. So let's say particularly for this image, we have considered there are four types of classes we are having, like grass, cat, tree, and sky. Right? So this is tree, this is sky, this is cat, and this is grass. You can see over here. So what is our task here? Our task is to provide the boundaries. Here we are not only providing the bounding box or the information about this, but also providing a boundary, precise boundary of the object. You can see over here. This is very, very important. We're not providing here the bounding box, but we are providing the exact boundaries of that object that is present over here. And we are also trying to assign a semantic category each of the pixel that is present in this image, and that is why the name is so called semantic segmentation. That means you are assigning a semantic category with respect to each of the pixel that is present in the image, right? So for each image, right, for each pixel in the image, you have to assign a semantic category. Either this belong to the sky category or cat category or tree category or sky category. That is what is semantic segmentation. But in case of instant segmentation is another type of segmentation, right? There are three types of segmentation we are having. One is semantic segmentation, where your task is just to assign a semantic category with respect to each of the pixel. But instant segmentation differentiates between the instance of the same class. Here you can see in this particular image, there are two dogs and one cat, but the semantic segmentation is going to tell, right? This is also dog, this is also dog. But in case of instance segmentation, right, the instance segmentation that differentiates between the objects of the same class. That means these are objects of the same class, but the instance segmentation is going to tell us this is dog one, this is dog two, right? So this is what actually this instance segmentation is all about, and how it is different from the semantic segmentation. I'll explain with another example also later on, right? So then how to just formulate this semantic segmentation problem with the help of or using deep neural networks? How we can formulate? So this segmentation can also be considered as grouping problems, grouping of similar type of pixels, right, in an image. So now you can see here, this is an input image. This is an input image, and this is the segmented output, or you can call it as an output image, where you want to only highlight the person or the bicycle, right? And there is another one which is known as background over here. And this particular problem of semantic segmentation can be considered as a pixel level classification problem. So previously, the kind of classification problem which you have solved is nothing but an image level classification problem, where with respect to each image, you can assign a label. But here, what I am actually trying to define here is, semantic segmentation can be casted as a pixel level classification problem, where every pixel in the image will be assigned to a semantic category. In this case, we are interested in person and bicycle, and rest others are going to be like background for us. So that means every pixel in this particular image is to be ultimately classified either into this person category or into the bicycle category or into the background category, which is black, you can see over here. Right? That is what we want to do. But this type of problem is little bit complex if you are trying to solve the problem with the help of learning based algorithms, or especially convolutional neural network and all. Especially if you are choosing supervised learning strategy, you are going to face a lot of problems. Why? Because in this case, the input X is an image and Y is also an image. Y is not a single value. Y is also an image. X is an image, Y is an image. And this image especially, that means Y is not a label, right? Labeling of different classes with respect to each of the image is little bit easier compared to pixel level levelings, or you can say pixel level annotations. So annotations at the pixel level is really difficult. That means for every pixels, for every image, pixel level annotations are required. That means this should be the Y. You see, for every image, you have to first compute this Y. It is of course a time-taking procedure, right? So X is an image, Y is an image, and again, here also you want to, right, learn a function which will map from this X to this Y, right? So I'm talking about supervised learning setup. So the supervised learning setup needs both X and Y is annotation intensive because Y is looking like this, right? So all the pixels has to be carefully annotated to design the model. So how to do this or how to solve this, right? Still, we are interested in this. Although this kind of problems or segmentation problems can be solved using traditional approaches, you might have heard about something called as thresholding, region growing, and there are a couple of such other techniques like k-means clustering is unsupervised. These are all unsupervised learning techniques. You don't need Y, right? If X is given, so you can just identify, or you can just find out the clusters. You can also find out the similarity of the pixels in the image, or then you can segment the image. That is what unsupervised learning is all about here. But these are not accurate, right? Because learning is even more powerful. But that's what we know, right? So that's why we're interested in learning-based segmentation methods, not these traditional segmentation methods. There is again a difference between instance segmentation and semantic segmentation. And there's something called a panoptic segmentation. So here are the three types of segmentations. That is semantic, instance, and panoptic. I hope it is clear to all of you, right? In case of semantic segmentation, if you remember, so every pixel has to be assigned a semantic category, and the category, the objects from the same class or from the same categories, right, are not differentiated here. But these are all like vehicles, these are all like persons, these are all like trees, these are all like road, and these are all like buildings and all. Fine. But in case of instance segmentation, you can see even in the same class, the objects are different. It is like person 1, person 2. It is like vehicle 1, vehicle 2. Right? So that means this instance segmentation differentiates between different objects of the same class. And it doesn't bother about the other. It only focuses on the important objects, and it just doesn't bother about the other kind of information which we have. And there is something called as a panoptic segmentation, which is nothing but the union of the semantic segmentation and instance-based segmentation. Fine. Yeah. So we have just now talked about the importance of these learning-based segmentation methods over those traditional segmentation methods which I have shown you. And these learning-based segmentation methods have achieved state-of-the-art performance and also led to performance improvements a lot of the times. And but the most important concern here is it is quite annotation intensive. Just now we have seen that it always needs a ground truth. We call it as a ground truth, right? These are like ground truth or mask. This ground truth is required, which is Y. The ground truth and Y is nothing but in the form of a mask here, which is again, right, having same size or same resolution with the input image. Next, we'll see the evolution of the deep learning architectures for solving segmentation task. We have seen the state-of-the-art architectures, convolutional neural network architectures for solving classification tasks, starting from AlexNet, VGGNet, GoogleNet, ResNet, DenseNet, and so many others. MobileNet, and there is something called as ConNext. Yeah. So there's a noise in the background. Can you please check? Maybe you can unmute your mic.
Gestational diabetes और डायबिटीज से इस टाइप के सिम्टम्स आते हैं फर्स्ट फैटी ब्लड रीजन फ्रीक्वेंसी
Yes, I'm getting noise in the background. Can you please unmute your mic, those who are sitting in the academy? Okay, fine. So next is the evolution of the convolutional neural network as well as the vision transformer models for image segmentation. We have seen these architectures, right? This is evolution of the CNN architectures used for classification task. This was, I mean, there's something called as LeanNet also, 1998, if you remember. AlexNet, 2012, the measure backthrow, right? And VGGNet, way back in 2014, GoogleNet 2014, ResNet 2015, and DenseNet 2016. Then you will find Convenext in 2022, right? So these are very popular architectures. You can call also the winner of the ImageNet challenge or ILS VRC challenge, right? So this is how we have seen the evolution of the CNN architectures used for the classification task. Now there's a question here: can I use the same architecture, whatever I've used for classification, to solve segmentation task? It is not possible. That is what we know, because in case of AlexNet and BGG, if you remember, the output is nothing but the set of probability values, and based on the maximum probability value, we used to decide the class level. But in this case, in case of image segmentation, it is a bit different. In this case, the output is an image, it's not a set of probability values. I mean, only related to the number of classes. Yes, of course, here also in the output, you will get the probability values, but the output should have the same resolution with the input. That is the major difference. So that means we cannot directly use these networks to solve, right? These networks cannot be directly used to solve the image segmentation task. So then how to solve this? How to design convolutional neural network to solve image segmentation task? We'll see. And here is the evolution starting from 2014 to 2020, 2022. But also there are a couple of such architectures available, right? In 2023, 2024, 2025, there are a couple of segmentation, you can say foundation modules that have been developed, like SAM, right? Segment anything model. These are prompt-based methods and all. So I will discuss also all these things, right? I'll show you some of the demonstrations, or you can say not exactly the demonstrations, right? If I get time, then I can show you the demonstrations of some of our models which are SAM based, right? I can, if possible, I will show you. Okay, fine. So let us also see the first architecture that was proposed for solving image segmentation task, especially semantic image segmentation, right? So for semantic segmentation, this was the first architecture that was proposed, and the architecture name is FCN, fully convolutional network. We'll see in detail how this network looks like, what are the changes they have made, why they have written VGG16 here, whether they have adapted VGG16 and then they have made modifications into the architecture or not, and they have applied, right? They validated their model on natural image datasets. At the same time, there are two other architectures which are very, very popular. One is SegNet and one is UNet, right? So UNet is the most popular architecture till date for solving any image and video segmentation task. And UNet was initially published in a medical conference, MICAI. I already mentioned you, right? I already mentioned in my last session that what is the importance of this MICAI conference, right? So in MICAI, so there was a paper called UNet. That means it's a medical conference. This method was initially validated on medical datasets, medical imaging datasets, and later been adopted to any field, any computer vision field, right? And that is why actually this field is very, very important, because this field has also, right, you can say, give a lot of image segmentation, or right, lot of image segmentation methods have been developed, right, where which were initially applied, or which were initially validated on medical imaging datasets. So you can see over here, there are a couple of methods available in the literature which were initially applied This is a medical imaging data set. This is a medical imaging data set. This is a medical imaging data set. This is a medical imaging data set, right? But these methods are very, very popular. If you go through the literature, you will find this unit is having more than 1,15,000 citations, right? So, I mean, that tells that how much accurate or how much, important this architecture is. And although it was initially applied on medical imaging domain, later been applied to several fields, right? So we'll see these three architectures especially, right, in this session, and then you can also, right, go through all these architectures, because these are the, you can say the main, you can say the most popular architectures, and if you can understand the, working principle of these three architectures or these 3-4 architectures, you can easily understand the working principle of rest of the other architectures. Very easy to understand, right? There's a deep lab. There is something called as attention unit. People have introduced attention into the unit architecture. Then they called it as attention unit. There's a unit plus plus. People have introduced some connections like skip connections into the unit architecture. They called it as a rest unit. They've introduced multiple, dense connections into the skip connections, and the convolutional layers also they've introduced. They called it as unit plus plus. There is something called as rest unit, as I mentioned, residual connections with unit. So all are like variants of unit only. That is how the unit is very, very popular, right? So let us start with the first architecture, which is known as fully convolutional network. And how this fully convolutional network looks like and how it is used to solve the segmentation task, right? So this is how, right, the whole fully convolutional network looks like, which adapted various classification networks like VGGNet, GoogleNet. So this is an example of VGGNet. So in VGGNet, if you remember, there are multiple variants. I mean, basically two variants of VGGNet we have. One is VGG16 and one is VGG. One is VGG16, one is VGG19, I think. Yeah. It all depends upon the number of layers, right? The VGG is having. Fine. But VGG contains 3 FC layers at the end. 3 FC layers. If you go through the VGG architecture, you will find there are 3 FC layers having 4096 neurons, 4096 neurons or nodes, and 1000 nodes in the final layer for solving the 1000 class classification task, right? But the name itself says here is fully convolutional network. Right? So what that is why what they did is they initially replaced all these 3 layers with 1 cross 1 convolutional layer. So here also 1 cross 1, here also 1 cross 1, here also 1 cross 1. But in the last layer, they have used 21 filters, right? 21. Why 21? It is actually C plus 1. There were 20 classes in that data set on which it has been validated, and 1 is for the background. That means every pixel in this particular image, right, or in the input image should be classified to either of these 21 categories. Either the first pixel will go to background or to any of the classes that has been defined in that particular data set. So the last 1 cross 1 convolution with C plus 1 number of channels is always mandatory to give the information about all the objects or all the classes which we have, right? But what we know that in VGGNet, there is, of course, a max pooling operation which is being used in the VGGNet architecture. So that means downsampling is creating a problem here. Initially, what they did, they replaced all these fully connected layers into 1 cross 1 convolutional layers. And then the last convolutional layer, if you look at here, and is having C plus 1 number of channels or channel dimensions, you can call it as, right? C plus 1, 1 for the background. And then there is a problem here. This also cannot solve our problem, because what we want in this case is nothing but an output image and having same resolution with the input image. But this is not going to give us that kind of output. So that means this downsampling operations are creating the problems. So what I ultimately want, if this is having size H cross W, right? What I want that my output, right? My output segmentation map should also have size, right? Should have an height value as H and width value as W. So how is it possible, right? How is it possible? So it's only possible by the upsampling operations. You need to upsample the output of the last 1 cross 1 convolution, and then you can get back the output, right? You can get back this output especially from here to here, right? You will not get this output directly, right? So this output you need to, you can say, post process, and you need to get this output by yourself, right? By just making few post processing steps and all, right? I'll discuss later on. So what is very important here is to understand what is this upsampling process here that has been adopted in FCN. So in FCN, they have adopted an upsampling process. Upsampling can be done actually in many ways. You might have heard about something called as interpolation techniques. There are different types of interpolation techniques like nearest neighbor interpolation techniques. There is something called as bilinear interpolation technique you might have heard about. There is something called as bicubic interpolation techniques. So these are not learnables. These are not learnables. These are like fixed interpolation techniques. But what they basically proposed in their work is, they proposed something called as a transpose convolution. Transpose convolution or op convolution to upsample, right, the output, the final output to the output having same resolution as the input. And the number of channels is still 21. I will tell you why, right? The number of channels is still 21, and why we do need, right, these 21 channels, I will explain, right? And what is this transpose convolution? Just you can say the reverse of the convolution operations, right? In convolution operations, when we apply convolution operation over an image, right? Let's say by using some filters having size, let's say 3 cross 3 over an 100 cross 100 image, right? This is a convolution operation. What we usually get is having size 98 cross 98. This is the output of the convolution if you are not using any padding and all, right? So that is the output which you get. That means the reduced version of the original X, right? So this is X. Let's say this is F. That's the filter. And what we are getting is X dash. That's the reduced size, right? X dash is having reduced size compared to X. But transpose convolution, right, will give you, right, the output, right, which is bigger than the input, right? That means it is perfect for solving the upsampling problem, right? So instead of using this interpolation techniques, what they suggested to go for transpose convolution, which is otherwise known as op convolution. So deconvolution is not the correct word to use over here. It has some different meanings in actually signal processing, right? And why do it actually, why we are interested in this transpose convolution? Because convolutions layers are learnable, right? And those interpolation techniques are not learnable. So what they basically did at the end, they have only applied one transpose convolution to get back the original image size over here, and the number of channels are still 21. So what is our task? If you remember, it is a pixel level classification task. Every pixel, as I mentioned, you should have a label. But how to get the label? Every pixel you will be having 21 values across the channel. That means for every pixels you will be having 21 probability values. Like in case of image level classification, you still remember every image you will be having different C number of probability values after using yes, after using the activation function. That's the softmax activation functions, you know that, right? Probability values with respect to each class 1, 2, and C. That was the pixel, I mean, that was the image level classification. For every image, you'll be having C probability values, and based on the maximum probability value, you will assign a level. But here it is a pixel level classification problem. For every pixel, there's a possibility that this pixel may go to background, or may also go to the 20 number of classes which we have. That is why there's a possibility that this pixel may go to any of the class out of C plus 1 or 21 number of classes we have. And based on, let's say, the last one is representing the background, right? If you look at this particular pixel, it actually belongs to the background. So definitely the probability value with respect to the last channel is going to be high, right? And rest others are going to be less. And if you add them together across this, you'll get a value 1, right? So for every pixel, you'll be getting 21 number of, for every pixels, you'll be getting 21 number of probability values. And then based on the maximum value, you will design the class. And then accordingly, you will assign the colors, different colors to different class. And what you will get, the output is in this form. That is what is required actually. And that is how actually FCN solved the semantic segmentation problem. I hope it is clear, right? Do you have any queries on this, how we are trying to solve a semantic segmentation task using fully convolutional network. Do you have any queries? Let us check the chat box. Oh, no, there's some problem. My side. Let us check the chat box. No, there are no queries till now. If you are having any queries, feel free to write them in the chat box. If possible, repeat. Which one? Can you specify which one? Which one I should repeat?
Yeah, told me, sir. So possibly they can write it down.
Yes, yes.
Table. If possible, repeat table.
Table. This table? Are you talking about this table?
Yes, S. Chandrasekhar, write it down whether you are talking about this table or
Is right? Yes or no?
differentiate.
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 A differentiate table? Which one? Can you elaborate it? Can you just elaborate which one you are talking about? Oh, different models. Yeah, I think this table, right? So then this is the table. We have not yet discussed actually all the models. So right now we are discussing each of the models, right? One by one. So I've just, which one is better? We have not yet discussed. We have not yet discussed actually all the methods. Let us first, discuss all the approaches and then I will tell which one is better. And you can also conclude, right? Which one is better. Let us first discuss all the approaches. I mean, especially top 3, 4 approaches. And then we will talk about, right? I mean, how people have improved all these techniques over the years. Fine. I'll discuss one by one, right? No need to worry. Is it possible to improve? Okay. From Pooja Chaudhary. Sir, is it possible to improve the segmentation accuracy using FCN? Using FCN, want to improve the, yes, there are multiple ways actually to improve these FCN architectures, right? Now you will see also how these FCN architectures have been improved or have been basically modified, right? And how people have come up with other architectures like UNet and SegNet, right? I'll talk about it because it is not at all a fully encoder decoder architectures. So for segmentation, what is required is the minimum requirement is like it should be an encoder decoder architecture, but FCN is not. Because in FCN, what we are doing here is only for one time we are applying, right? You can see over here, we are applying the upsampling operation only for one time. So from here, you are directly applying upsampling operation, right? To get the output resolution equal to the input resolution, right? So this is actually the major concern here. So can we have, I mean, some type of encoder decoder architectures where, right, the encoder will be like the mirror of the decoder architecture. I'll discuss, right, one by one. Let us first discuss SegNet. Again, I'll come back to your points, right? like whether which one is better and how to improve the performance and all. So for that, actually, we should understand the limitations and the weaknesses of this kind of approaches, right? So this is actually one of the weaknesses, as I mentioned, that there is only one that you can see over here, whatever I have mentioned. There is only one final upsampling layer to get back to the original size. So instead of one, can we have same number of upsampling layers, right? Like we have downsampling layers in the encoders. So we have multiple downsampling layers, right? We have multiple downsampling layers. So can we have same number of upsampling layers at the decoder part? That is what is actually the encoder and decoder part. And the very first encoder decoder architecture that was published is nothing but SegNet. It was actually initially published in 2015, but later it has been appeared in one of the top journal we have in computer vision and machine intelligence, which is IEEE PAMI in 2017, right? But the idea was released initially, right, in 2015. You can see in the literature, right? So you see how this architecture looks like. It looks very uniform. This is the first encoder decoder architecture. It is also fully convolutional. Fully convolutional encoder decoder architecture. You see here, this part is encoder decoder. Now the question is, from where we'll get the decoders? There is no FC layer. You need not even convert those FC layers into one convolution. So they have directly taken all the convolutional layers from the VGGs. So this is like, this encoder is nothing but the VGG without FC layers. There are 3 FC layers. Just remove the 3 FC layers and take all the other layers, right? And the decoder is just the mirror of the encoder. You can see over here. The decoder is the mirror of the encoder, where there are some upsampling operations. You can see in green color, they have mentioned the pulling operations. These are all downsampling operations, right? You will also find the same number of stages in the decoder and the same number of upsampling operations. Upsamplings are not done with the help of transpose convolutions in case of SegNet, right? Because transpose convolutions again takes a lot of parameters. So that was their idea. So no need to even take transpose convolutions here in the decoder. Later you will find its applications of the transpose convolution in unit architecture, right? But what they basically did is store the pulling indexes or the winning indices during the encoding process, right? They store the winning pulling indices, right? I'll show you with one example that what do you mean by storing the winning pulling indices and using those indices upsampling, right, the feature map in the decoder, followed by some of the sequence of the convolutional layers, right? Mostly whatever the output you will get is sparse in nature. To make it dense, they have applied multiple convolutional layers, right? Very similar to the decoder, I mean the encoder process, right? You can see over here. Fine. We'll see, because what is the main contribution here is to design a decoder architecture, of course, and decoder architecture. At the same time, they have also proposed something called as, a new upsampling technique, where your task is to store the winning pooling indices during the encoding process and use those indices, for upsampling the feature map in the decoding process. That is what they have done, right? Let us try to understand how this upsampling is performed in the decoding process in the SegNet architecture. Let's say this is, when we are trying to upsample, let's say this is a 2 feature map which is given to us, and you want to upsample this to 4x4, right? Because this is upsampling. And in case of, in case of downsampling, if there is a 4x4, if there is a 4x4 feature map given to us, and then you can just reduce it to 2x2, right? Let's say using max pooling. So what we usually do in case of max pooling, you need to first identify the size of the filter, or you can say the size of the mask. You can say if it is 2x2 and the stride value is 2, then only you will get size having 2x2 from a 4x4 matrix, or from a 4x4, you can say, feature map, right? So this is actually the window size 2x2, right? This is again 2x2. Again, this is 2x2, and this is again 2x2. So from each of these windows, you used to find out the the maximum values out of this 4, And what I'm trying to say here is while finding out the maximum values, try to also save the pooling indices. Let's say this one is maximum out of these 4 values, and this position is 0, 0, this is 0, 1, this position is 1, 0, this position is 1, 1. So that means you have to only store the indices. So for this, 0, 0 was the index, and for this, let's say 1, 0 is the index. Yes, actually this is 1, 0, right? And for this, let's say 0, 1 is the index, this one, and for this, let's say 1, 0 is the index. So you need to only store these 4 index, right? These 4 index, that is 0, 0, 1, 0, 1, 0, 0, 1. You look at here. This is actually the index which you have stored in the memory, right? While doing this encoding process. And now we will use these particular indices to upsample the image or to upsample the feature map in the decoding process. How is it possible? You see here, this is the input feature map, which is 2 cross 2. All right. And it is saying that the winning index at that time was 0, 0. So you need to place this A in 0, 0 position, and rest other values are going to be 0. That's why I said that what you are going to get is nothing but a sparse feature map over here, right? And then in case of 1, 0, you look at here, in case of 1, 0, so this B has to go to this particular position because this position in this particular window is known as 1, 0, right? So likewise, you can complete the whole feature map over here. So this is how actually they solved the upsampling, right? Or I mean, they solved the upsampling problem, right, without using the transpose convolution concept in SegNet. And they claimed that this is performing better than the traditional fully convolutional network, right, that was proposed earlier. I hope it is clear. The upsampling is very easy to understand here. So you need to only store the max pool indices. I mean, where there's a, you can say it's a winning indices, right? I mean, I've just explained what exactly is this. Fine. And at the end, finally, at the end, you'll be having one cross one convolution with how many channels? Of C plus 1 number of channels. This will be there always because ultimately you want to get 21 number of, right? 21, why? Because this data set contains 20 number of classes, right? So this varies from data set to data set or from data to data or the kind of problems which you are solving, right? The number of classes you are dealing with. Fine. Okay. So 1 cross 1 convolution, C plus 1 times. That will always be there in across all types of architectures because the goal is to get 21 number of or C plus 1 number of probability values with respect to each of the pixels in the image. That is what is our goal. So that is why this is going to be fixed for every architecture. Now let us about very popular, the most popular architecture, which is known as UNet architecture, right? So before we discuss all these points, let us first look at how this architecture looks like. You can see here how the architecture looks like and why is the name so-called UNet. It looks like the English letter U. You see here, it is again an encoder-decoder architecture. This part is known as encoder. This part is decoder. They call it as contracting path. And then they call it as an expanding path, right? In the encoder, you will find some convolution operations followed by max pooling. Again, convolution operation followed by max pooling. This process is repeated for a few times, right? And in the decoder, you will find something, you will find some interesting things, right? In the decoder, upsampling, right? They're again not using the, pooling indices and all. They're using the op convolution concept. You can see over here, the op convolution. So this green color arrow mark here, upward arrow mark, is nothing but the op convolutions. That means they are using in the decoder, they are using what they are using is nothing but the transpose convolutions for upsampling the feature map in the decoder. But the most important contribution they made here is they have introduced something called as an skip connection. So these are the skip connections they have introduced, right? From the encoder to the decoder. You can see over here, there was no skip connections in SegNet, if you remember, right? Only we were storing some of the winning indices for performing upsampling, but there was no connections from the corresponding layer in the encoder to the decoder. So that means what we're trying to do here is, after performing the upsampling operation, this decoder, every stage in the decoder is the input from the encoder, the corresponding encoder path, and this actually creates a huge difference in the performance, right? And this also helps in improving the localization of the, or you can say this helps in preserving the localized informations of the objects that are present in the image. And this is not only the contributions, they've also proposed some loss functions, right? I've not yet discussed about loss functions and all. And they've also proposed some loss functions. And because medical images are always having multiple pathological regions or multiple lesions, and now sometimes even the lesions are overlapping with each other. So they've also proposed something how to deal with those kind of issues and all. But at the end, finally, you will be having again 1x1 filter with C+1 number of channels to have 20, or you can say 20C+1 number of probability values with respect to each of the pixels that is present in the image, right? Fine, and these are some of the points, right, which you can note it down. This is very, very important, right? It's not corrections, it's connections, right? Skip connections or residual connections. To understand this concept of skip connections, right, you can go through this paper, residual connection. That is where actually the residual connections, that is where actually the residual connections or skip connections were introduced. This is the paper, right, where you can see in early, convolutional neural networks, people are only using convolutional neural networks, right? Convolution, let's say this is convolution, right? But in this, basically in the ResNet, they propose something called as a residual block. This is how actually the residual block looks like. You can see over here, right? This is a skip connection. This is a convolution operation followed by another convolution operations. And then again, you are reconsidering the previous input and you are adding it to the final output of this after convolutions, right? That means you are trying to reuse the feature, whatever you have already obtained just before these two convolutional layers. And this is, what is called as residual connections or skip connections sometimes. So it is basically used for feature reuse, very, very important. At the same time, the skip connections are also useful, right, for, addressing the vanishing gradient problem. Or the vanishing gradient issue in the architecture. Sometimes, if the network is more deeper, the gradient may not flow through, right, the deeper architectures, right, may not reach the first one because you need to ultimately back propagate the errors, right? So while back propagating the errors, sometimes maybe the error, or sometimes maybe the gradient value may become 0 because it is a very deep architecture. In that time, the gradient may take this path in place of this path, right? So there are a lot of such residual blocks. So this forms a residual block. There are a lot of residual blocks you will find, right, in the residual network, especially ResNet, right? And that is where actually this residual connections were introduced, and then they have used it, right? For feature reusing and all. So that means you are again reusing the features that you have obtained in the encoder process. And this helps in preserving the important semantic informations that the image is having, right? I hope it is clear. And still, I would recommend you to go through the paper once again and try to find out the importance. I've already mentioned the importance of these skip connections. One is like feature reuse, and another one is vanishing gradient issues, right? And also there are a couple of other things which I mentioned, right? So if you want to know more details of this, please go through the paper residual connections. You'll get all the details, right? Very, very important. Fine. So as I mentioned that, yes, there are different variants of unit architecture that have been proposed over the years. We'll see a couple of such architectures, but at the end of at the final layer, you will always find convolutions with C+1 number of channels, right? That is what you will always find. And upsampling here in this case is performed with 2x2 transpose convolution with stride 2 and padding 0. This will actually help us in simply doubling the input map dimensions. That means if you are having input map, if you are having input maps with size, let's say 4 cross 4, and if you are applying transpose convolution, T convolution, right? And if you have to, if you can choose these parameters here in this case, I mean like 2 cross 2, the size should be 2 cross 2, and the stride value should be 2. So this is going to, sorry, this is 4 cross 4. This is going to give us the output having size 8 cross 8, right? 8 cross 8. So I mean, this is sometimes very, very important, right, for us. How to get the double version of this, or you can say double size of the input mechanism. So these are some of the parameters which you need to remember, right? Or you can also design your own architecture by using these concepts and all, right? Fine. So why actually we're preferring, or why people are Yes, am I audible? Am I audible? I got disconnected.
Yes, sir, you are audible.
Okay, let me reshare my screen. Is my screen visible? Can you please let me
Yes, sir,
know?
visible. It's visible,
Okay.
sir.
Thank you very much. Yeah. So one thing I would like to discuss here is what should be the loss function, right? Here in this case, right? So the kind of loss function. Can you tell me what kind of loss function we use for solving classification problem using convolutional neural network or traditional neural network as well? Do you know what kind of loss function is used for solving classification problem? Please try to write your answers in the chat box so that I just want to, yeah. Okay, binary cross entropy. If there are two classes, right? If it is, if very good. So thank you. If the number of classes are more, we use categorical cross entropy, right? That's what you know, I hope. If the number of classes are more, we use categorical cross entropy, right? So cross entropy is the basically cross entropy is the loss function which we used for classification problem. Now the question is, what should be the loss function in this case? Right? In case of segmentation, how to compute the loss function? And there is a question also here, why cross entropy? Why not mean square error? Why not mean square error in case of classification? Then we'll come back to, right, a segmentation task. In case of classification, what you remember is given a set of images, there's a set of images given to us, and here is the CNN architecture. And finally, what you are getting is a set of probability values. For 1 to C, there are a lot of probability values you are getting, and I can just call it as a Y cap, right? I can call it as Y cap. And what we know, this is a kind of probability distribution. So Y cap is a kind of probability distributions I'm having, because these are all probability values, and if I add them together, this is going to be 1. If I add these probability values, if what I'll get is nothing but 1. So this is one probability distribution. And what I know that if this is X, right, this is image number X, or image, there's X1, there's X2, image number 2. Every image you'll be having a label. X1 is having label Y1, X2 is having label Y2. But to solve the problem, we know that we need to first encode these levels into its corresponding one hot encoding, right? If there are 3 classes, for example, 1, 2, 3, I need to first represent, right, the class 1 as 100, class 2 as 010, and class 3 as 001. That is what you know, right? So these are like the labels. You can say one hot encodings, and this can be again considered as a probability distribution, which is y. Y is the target value, or y is the desired value. This is a probability distribution, and this is another probability distribution, right? And you want to find out the difference between two probability distributions. Mean square error is something very different, which is usually used for regression task. Where you want to check how much y cap is deviated from y. You are not looking at how much y cap is deviated from the y value. Rather, you are trying to deal with two probability distributions. Find out the difference between two probability distributions. What we have is nothing but called as cross entropy. This has been actually derived from something called as relative entropy, right? Which is otherwise known as scale divergence. I hope you know all these things, right? So, but cross entropy is basically used to find out the difference or the distance between two probability distributions, which MSc cannot do. That is why cross entropy is useful in classification task, right? And that is why we use cross entropy loss. And the formula is very simple here. It is like yi log of yi cap, where I varies from 1 to c, right? So this is what this yi is values are nothing but 1 or 0, and this yi cap is nothing but the predicted probability values for each of the class. That's the formula for the categorical cross entropy. If it is a binary cross entropy, right? So the case is something different. You'll be having two classes. You have to use sigmoid activation function at the end, not the softmax activation function, right? That is sufficient to solve the problem. Fine. If you are having two classes, even you can go for softmax. You can have also two nodes to solve the classification task. That is fine. But in this case, especially because our main focus is segmentation today, now the question is how to design a loss function for the segmentation task. Here, for every pixel, you are getting 21 probability values. And you know also that pixel should belong to background or class 1 or class 20. That means every pixel has to be represented, or every pixel will be having 21 or c plus 1 number of probability values. Every pixel, you will get c plus 1 number of probability values, and there is also one target probability values. Again, you are having two distributions, right, for each of the pixels. So then what I can say here is you have to compute the loss for each pixel, right? And the loss function is nothing but sum of pixel wise. Otherwise, mostly it is written only cross entropy. So, right, if you choose the loss function, if you are trying to implement the same using either PyTorch or TensorFlow, right, you can only mention it is cross entropy. But what is exactly happening is nothing but sum of pixel-wise cross entropy. For every pixel, you will get a loss. Then you take the sum. Then you will get the whole loss of the particular image. I hope it is clear, right? That's the loss function here. That is not only the one loss function, the simplest loss function I'm talking about. There are also, of course, different types of loss functions we have. Okay, let us now look at some of the variants of the unit quickly, and I'll show you also the applications in my next sessions. I mean, there are also two sessions which I'm planning to take. So in those sessions, I will be talking about the applications of this kind of architectures and the kind of architecture which we have proposed, right? And what are the limitations we have observed in the existing architectures, why we have developed some of the architectures and all. Also, we have some papers in MICAI where this unit was proposed this year, right? So we have also a paper in MICAI. So I'll also explain all those things later on. Fine. But now we just see how people have modified these unit architectures to have new architectures, right? So based on this, you can also think of designing your own architectures. So what people have done initially, that people have just introduced a residual connection. You can see over here convolution I mentioned earlier, and there is a skip connection here. This is the addition operation. People initially in the unit architecture, there was no, if you look at here, there is no skip connection here. So what people did, they just introduce a skip connection in each of the block of the decoder, I mean in the encoder as well as the decoder, right? And that is how actually the developed residual unit is really very, very popular. And they claim that this is performing well, right? Then unit architecture. Later, what people have done, people have also introduced the convolutional layers in the dense connections across the skip connections we have. They have got something called as unit plus plus. It is again a part of it is again published in MICAI 2018, right? You can see. Then people have okay. There is one more architecture, right? People have also identified that yes, FCN cannot capture the features, or you cannot deal with or cannot segment the objects having different size and different shape because of its limited receptive field. So that is why people have come up with one architecture known as pyramid scene parsing network. Again, it is published in 2017 CBPR, right? So what was their idea? The idea was very simple. The idea was to first get the feature map from any architectures like Resonate and all. After getting the feature map, right, what they did actually, they applied something called as a pyramid pooling approach. Pyramid pooling approach, like they have initially applied global average pooling to get the output in terms of values like 1 cross C, and then they have applied again successive pooling operations to have the values 2 cross 2 cross C. Let's say it is H cross W cross C, right? They've applied global average pooling, different types of poolings, right, to have the outputs having size difference like 1 cross C, 2 cross 2 cross C, 3 cross 3 cross C. It is like successive. You can say they've applied different types of pooling operations over the same feature map that has been obtained from any pre-trained CNN architecture like ResNet, VGG, whatever, right? And then what they did is after actually getting the outputs after applying this different pooling operations, like they call it as a pyramid because they've applied different size of pooling operations, and ultimately they're getting the outputs like 1 cross 1, 2 cross 2, 3 cross 3, and 6 cross 6, like that. And after that, because pooling doesn't reduce the number of the channels, right? And their plan was to actually concatenate all these outputs together. And even after concatenation, the number of channels is going to be 4C, because here it is C, here is also C, here it is C, here it is C. If you just concatenate them together, even I mean, you cannot directly concatenate them together, right? Because the size is different. You need to also perform upsampling over here, right? Then you can perform concatenation. But before that, what they have applied is a 1 cross 1 convolutional layer. And this is a kind of, bottleneck layer they have used over here. And this 1 cross 1 convolution, basically they have used to reduce the number of channels from C to CY4. C to CY4, you can see over here. And then they've applied upsampling operations, especially they use bilinear interpolation over here, right? In place of transpose convolution, and in place of preserving this winning indices, pooling indices and all, they have simply applied bilinear interpolation to upsample all these outputs of different pooling operations. And we all know that after upsampling, this resolution, basically the spatial resolution size is going to increase, but this is not going to the what I can say is the change, right? That means the C/4 will remain the same. And after concatenation, what they will get is nothing but C/4 4 times concatenations. You'll get the final depth is having size, the final channel is having size C, and upsampling has been performed to get back to the original size. And then they finally performed something called as a convolutional, of course, 1 cross 1 convolution, having C plus 1 number of channels to solve the problem, or to have C plus 1 number of probability values with respect to each of the pixels. See, it is also another contribution they have made. Only they have introduced something called as a different types of pooling operations, and then they have followed few steps, right, to have the compatibility with segmentation architectures that have whatever we have seen earlier. People have also designed several other architectures. I'm not going into the details of this. So this is another architecture, right, which is known as attention unit. We have seen today attention mechanisms. People have introduced attention mechanisms into this key connection. You can see over here, these are all attention mechanisms, and they have called it as attention unit just to focus on the important part. And it was initially again applied on the pancreas data set. We can see over here, right? The goal was to learn, right, to suppress the irrelevant regions and highlight the salient features which is useful for this kind of task, pancreas segmentation and all, right? That's why people have used, attention mechanisms into the unit architectures. And this is one architecture which is developed by one of my friend, Dr. Jha, right, Devesh Jha. So you can see over here what they basically did in their architecture is they have introduced, of course, a skip connection over here. It is just an extension of the residual, unit architectures. They've just introduced, you can see over here, they have just introduced something called as a squeeze and excitation block. Today only we discuss what is squeeze and excitation block, right? So it is like these all attention mechanisms are like plug and play module. It can be plugged up to any blocks, but you need to also think about that because these are such modules which also introduces some of the parameters, right? It should not happen that after introducing the attention mechanisms, your accuracy should not be dropped, right? So that means because of the introduction of the huge number of parameters, you need to be very, very careful where to use or where to integrate all these attention mechanisms into the CNN architectures and all. So you can see over here, so they've only introduced the squeeze and excitation block, right? You can see over here, squeeze and excitation block. And here they have used a pooling block over here. And then they have, called it as something called as a res unit plus plus. It is also very popular architecture, right? Fine. There are also architectures based on, vision transformers. Here is a fast architecture on vision transformer. Unit R you can see over here. So they have, in the encoder, you will find they have applied something called as a transformer, and then they've applied some convolution operations in the decoder to get the outputs, right? So it is a transformer-based architecture. There's one more transformer-based architecture which is very, very popular, is known as trans-unit architecture because it is a patch-based. And here in this case, they are not directly computing the patches and upon which they are not applying the self attention and all. So what they're trying to do here is they're initially applying the convolutional neural network and trying to get the patches from the convolutional neural network and then send the patches to the transformer layer. And then again, during decoding process, they are also taking the outputs of the corresponding encoder layer of the CNN, and this is the output from the decoder layer, and this is the output. This is the input they are taking from this corresponding CNN layer, and they are combining them together, pass it to a convolutional layer, following the same procedure for every step of this particular architecture known as trans unit, and they've claimed that it is performing well compared to all possible types of architectures, whatever we have seen till date, right? There are also a couple of other architectures you will see in the literature, right, related to transformer and all, right? Here are the two different architectures, very, very popular, right? Discuss all these architectures, like it takes a lot of time to discuss all these architectures, right? So it's difficult to discuss all these architectures within a given time, like within 2 hours or within 1 hour of time. So here is the set of loss functions, right, which have been popularly used for solving segmentation tasks. So that's the cross entropy loss which we have discussed, and there are also different types of cross entropy loss. And you can say focal loss is very, very important. Dice is very, very important in case of what I can say, segmentation task and all. So the kind of actually performance measures we use in this case. In case of classification, we basically use, if you remember, accuracy, F1 score, sensitivity, specificity, again, precision, right? So these are some of the performance measures we use for classification tasks, for evaluating the classification models and all. But for evaluating the segmentation model, we don't prefer to use accuracy. Accuracy is like how many pixels are correctly classified, right? Even if, let's say, not not a single pixel, right, from the foreground is correctly classified, all the background pixels are correctly classified, which is black, right? So that means you can also say that yes, my model is this much accurate, but it is not correct in case of segmentation, right? So the kind of there are 2-3 you can say popular measures which we use to evaluate the segmentation models are nothing but dice coefficient, very, very important. Intersection of a union is also very, very important performance measures we use to evaluate the segmentation models. You can go through this and you can get all these things, right? Fine. Okay, so the case studies actually I will discuss, in the corresponding, and I have, I think, two other sessions. So in those sessions, I have a special session on colorectal cancers. So I have also a few case studies on colorectal cancers here. I'll be discussing all those case studies in that particular session, and there are also a few case studies on retinal imaging that I'll be discussing on the session on retinal fundus image analysis and all, right? We'll also discuss some of the challenges at the end. I mean, there are a couple of challenges we are facing while using this kind of segmentation approaches. So how to deal with those kind of challenges also we will discuss in the next session, right? If you are having any queries, right, so I'll be happy to take it. You can write it. You can write them in the chat box. I'll be happy to take some of the questions, right, which you might be having. So now, if I see questions once again, right? Yeah. Yes, sir, we have worked on it, but its performance is not improving. Which one? Yes, sir, we have worked on it, but the performance is not improving. Yes, Pooja Chaudhary, can you please tell me which one you are actually? Okay, which one it is related to? Which question? So you can just write rewrite the question, right, in detail so that I can explain you better. And I think we have discussed a couple of approaches today, right, for segmentation, right? Very, very popular architectures. Now you can go through even several other popular architectures which have been recently proposed, right? There are also different types of foundation models people are right designing nowadays, and it is very, very important. But it is again you will find some difficulties in adapting those foundation models, right? Because ultimately you are going to fine tune all those models, right? Because the domain is different. And the transfer learning process also, which we discussed yesterday. Okay. Yeah. So if you are having any queries, you can write in the chat box.
Yes, participants, if you have any query, please drop at chat box. Okay. It seems that, sir, there is no query.
Yeah, yeah. You can wait for 1 more minute.
Okay.
Maybe they're typing. Otherwise, we can stop. Any implementation of the models? Yes. If you want, I can share the code with you, right? And otherwise, what I can do is I can show you some demonstrations in the next session, right? I mean, on UNet and all, how to implement these UNet architectures and all. It's very easy actually to implement if you have implemented the convolutional neural network models. So then it is very easy also to implement the UNet architectures and introducing some other things like attentions, residual connections, and all. So I'll try to show you the demonstrations in the next session. That would be great if you could. So of course, I will do that, definitely. So I'll first do the demonstrations, and then we'll go for the the next topic and whatever I want to discuss.
Okay. So,
Okay. I
thank
think
you.
that's it for today. Thank you very much, all of you, for your attention and for your patient listening. Right? How it's different from MATLAB based on okay, okay. Yeah. So the problem is right now actually, why actually we are preferring right. What you can say, the Python based tools, right? Especially the tools like PyTorch and TensorFlow over MATLAB. There are several reasons, right, why we're not following this. Because it is not at all free, and it takes a lot of memories or even on the computers. At the same time, most of the latest approaches, or you can say the functions that are required to implement all these algorithms or and all, are available on those kind of tools, right, which can be easily integrated into Python, right? So that is why actually we're preferring this. But if you want, you can also implement the same using MATLAB. But the kind of demonstrations which I'm going to showcase you tomorrow is, of course, will be on either PyTorch or on TensorFlow, right? It's even not that difficult to learn, TensorFlow and PyTorch, right? Fine. Okay, so I'll stop here. Thank you very much once again for attending the session. So see you tomorrow. Good night.